Good morning, good afternoon, good evening, whatever time it might be when you're looking at this accuracy assessment lecture. Accuracy assessment is one of the most important parts of remote sensing. We looked at classification analysis, and many analyses that are done in remote sensing have to do with classification. But once you've finished your classification, how do you know that it's worth trusting? Here's a very interesting classification. This was done in 1988 for Western Oregon. This map has been updated numerous times since then, and it's a forest type map for the Western Oregon, west of the Cascades. It consists of a number of miscellaneous classes: cloud and shadow, snow and ice, water, urban areas and highways, agriculture, and other non-forest areas. These are all gotten through a variety of methods, mostly relying on GIS and a few simple rules. What we're interested in here is the forest. And the reason is that at this time there was questions about the extent of old growth forest, where it was, how much there was, and that was all going into real world management decisions about the northern spotted owl and to a lesser extent the marbled murrelet. And so the forest classes are the ones that people are really interested in. Open forest, that is less than 30% vegetation. Semi-open forest, 30 to 70% vegetation. And then closed forest, greater than 70% vegetation cover. Among those closed classes, we have broadleaf, that is greater than 70% broadleaf cover. We have mixed forest, so between 70% broadleaf and 70% conifer cover. And then among conifer covers, and this was the really important part of the analysis, young forest, mature forest, and old growth forest. And it was that old growth forest that they were most interested in. Now this looks great, and if you look at it as someone who understands Western Oregon, you think, it looks pretty good. I mean, we've got mixed forest and broadleaf forest on the west of the Willamette Valley, the Willamette Valley being that big gray area that sort of goes up in a north-south direction, more or less. Very little conifer forest because they nailed that area. The Siuslaw forest just chopped down everything. They were exporting something like 1 trillion board feet a year, and a board foot is an area that's, what is it, a foot by a foot by a foot? It's a lot of wood. Whereas most of the Willamette side, that eastern side of the Willamette Valley, was under much more serious protection. And also, honestly, it was just had higher slope. So it was more difficult to get in there and log, particularly at the highest elevations. So this looks good, but we talked about when we were talking about vision, your mind is really good at pattern analysis, but to some extent it's too good at pattern analysis. That is, it can pick up patterns and sort of see a template of patterns where there really isn't any. And so the only way to figure out whether or not you're doing a good job of an accurate job of classification is to actually go in and do this accuracy assessment process. So this is one of the most important steps in any classification exercise. It should never be, no classification exercise other than things that you're doing as a lab should be considered complete without an accuracy assessment. Without an accuracy assessment, the outputs or results, they're really of little value because you don't know whether you have information that you should be able to take action on. You might be going out and making management decisions based on completely incorrect data. And there was a period in the late 1980s where consulting firms were going out and using Landsat data to do classifications on national parks. And they would come up with all sorts of very fine detailed classes. You know, they were saying, well, this is Douglas fir ponderosa mix. And they would have another class that was, you know, more ponderosa than Douglas fir, and another one that was more Douglas fir than ponderosa pine. And ultimately, when people went out and looked at the ground truth, looked at the actual accuracy assessment, they realized that it was all a bunch of garbage, and that they were essentially worthless classifications. Now, here is a good example of taking lemons and making lemonade. The people who were sort of at the forefront of making these screw ups then turned around and became people at the forefront of implementing accuracy assessment. So, you know, just because you screw something up doesn't mean you can't go around then and lecture and write books about how you shouldn't screw up the way you do it. So there are a number of aspects of map accuracy. You know, there's accuracy associated with the field data. So positional accuracy, whether or not you actually are where you think you are. There's attribute accuracy, excuse me. So you might be collecting species data and you could have the wrong species. You can have measurement accuracy, so you might be measuring the diameter of trees and screw up your measurement. There's classification accuracy, and that is the accuracy that we're going to talk about, and it's whether or not you have correctly identified the classes that are there present in the field. And there are more advanced accuracy assessment approaches. So for instance, you might be interested in understanding whether or not you got the boundaries between two areas correct. So you might have to the west some broadleaf forest and to the east a field. And in normal accuracy assessment, we would do the assessment based on areas away from the edge, mostly because it's super hard to get edges. But you might be interested in where the boundaries are. So you'd have to go and do a specific analysis. We normally don't do that. Normally, we just want to make sure we got the classes correct. So in thinking about accuracy assessment, we need reference plots. We need plots in the field where we know that we can tell what the classes are. And I'll return to this over and over again. It used to be reference plots had to be plots that you actually went out to and did some kind of classification, like using a dichotomous key, for instance, or doing a visual key. But because high spatial resolution imagery has become so much more available, and many things that you're interested in, like species composition and tree cover, are discernible from this high resolution imagery. Many times we're talking about doing accuracy assessment from photos and not from field data. So you have to have a match between the spatial scale of the remotely sensed data and what you're observing in the field. So one thing that you have to think about is your GPS ground plots. So if you have a GPS ground plot that you've GPSed, that is, you've gotten its corners, and each one of your plots are 5 meters on a side, that may not be very useful if your remotely sensed cells are 1 kilometer on a side. Okay, so we've made some measurements in the particular pixel of interest, but we have no idea if we've captured the variability of the 1 kilometer pixel. So you may need aerial photos or even other satellite images in order to do that work. And you may actually need multiple levels. So for instance, you might go out in the field and take some field measurements, match that up with some small pixel spatial, high spatial resolution imagery, and then summarize that high spatial resolution imagery at a resolution that you can use with, say, that 1 kilometer spatial resolution imagery. And so you have to take into account spatial frequencies of the image and the precision of your field and image locations. So for instance, example 1 there shows low spatial frequency and, more or less an image with homogeneous patches. And in that, we have just a simple box representing a particular scale of sampling, and that scale, it's whatever, 8 out of 9 boxes are one class and 1 of the other boxes is another class, and that may be useful for what we're doing. Example 2, you could have high spatial frequency, so a heterogeneous image. And so your sample there may not be associated with any particular class. It's going to be a mix of classes, and that mix may make sense if they're very similar, but if they're very dissimilar, then you're in trouble, because you now have a mixed class, and it's very hard to do a classification that involves non-mixed classes if you now are using mixed classes. It's very difficult to characterize every kind of mixed class you could be getting. So we have some concerns about the size of the samples that we're going to be making to try to determine class. We also have to think about sample design. So the accuracy assessment sample design just describes the distribution of the validation data in space. So are you going to lay out your samples evenly in north and south and east and west? And are you going to have different distributions based on the identity of the class? So a number of sampling techniques can be used. Some of them are random, systematic, non-aligned, stratified random, and clustered. And this just gives you an idea of what those little approaches look like. Okay, a little interruption from my 7-year-old. I don't remember exactly where I was, but here's a graphic of the different kinds of sampling that you can use. So only random sampling designs can guarantee an unbiased sample. So random sample design, you would simply use a random number generator and use it to pick positions within your study area. You can just do this in Excel. And it's the only one that guarantees an unbiased sample. You know, you're going to wind up with no spatial biases as a function of doing this random sample approach. However, the design is inefficient because it doesn't sample rare cover types as frequently as common ones. So if you have wetlands in your study area and they make up 5% of the land cover, then 5% of your samples are going to fall in wetlands. And so you may have to sample a lot of points to ensure that you get adequate sampling of a rare cover type. Conversely, you sample so many points and you're going to wind up with a ton of points in something that you've got a lot of on your landscape. And so you might not need that many for conifer forest. It's just overkill. But that's the constraint of using a random sample design. So a systematic sample is actually the least useful design. So this approach to sampling it just lays out points on a grid. And that is great from the perspective of you don't have to worry about whether or not you're sampling throughout your scene, but it may result in a sample distribution which favors a particular class depending on the distribution of the classes within the map. So for instance, you can imagine that in the western United States, where we have our land cover laid out in a regular grid over the agriculturally productive areas and also rangeland, that you might wind up with your grid lining up with roads in a particular area. And so what all you're going to sample is roads. Well, that's not really helping you. In a systematic non-aligned sample, the grid provides an even distribution at a coarse scale, and samples are placed using random or stratified random. So you would say, okay, we're going to have a mile by mile grid. Within that grid, you're going to have randomly associated or stratified random associated points. I'll talk about what stratified random is in a moment. And here is that moment. In many instances, the stratified random sampling strategy is the most useful. So in the case where the map area can be stratified based on a systematic breakdown, so that could be an agricultural map, it could be a geological map, it could be an unsupervised classification where you say, well, we know what the spectral classes are, let's sample the spectral classes in some sort of random way so that we can tell what each one is, and then we can go back, get rid of the unsupervised classification, and do a supervised classification using the data that was collected using that random sample design in each of the systematic subareas. So the use of this approach ensures that you have adequate cover for the entire map, as well as generating a sufficient number of samples for each of the classes on the map, including rare ones. So to go back to an earlier example, if you had 5% wetlands on the landscape, presumably you would pull out those wetlands using an unsupervised classification, and then you could assign a certain number of points to those wetland areas. And you might find that they're all wetlands and they're all very similar, or you might find that there may be 2 or 3 classes that you would find within that area, and those would then become part of your classification scheme. Now we come to cluster sampling. So in cluster sampling, you randomly place cluster centroids, okay? And you then use those as starting points to sample several nearby observations. And both the centroids and the sample points can be randomly selected, stratified, etc. You can use all the other approaches we've talked about, but we're going to start with randomly placed clustered centroids. Well, why would you do that? Because it's very efficient for large study areas where car travel will be necessary. So we use this on a project looking at the Hyde Park fire, and you could put points out 5-10 miles in a study area, but the truth of the matter is that that's very difficult when in our case the roads were blocked. It was a long way to hike, and so the thing that made the most sense was to find centroids that we could access and then set out individual plots using those centroids as the center point. So now we have an idea how we're going to put samples out on the landscape. The next question logically is, how many points do we need? So we need a number of samples that can be sufficiently large to be statistically representative of the map area. The number of points you're going to need does depend on the sampling design used. Now, of course, there are also practical problems involved with this, because generally you don't have an infinite amount of energy and money to put into the sampling. There's only so much you can ask a graduate student to do. I know, because I've tried, and yeah, they eventually break down. So you can calculate the number of points once the following is known. If you need to know the approximate accuracy you expect your classification to have. So you might say, based on previous results, we expect this classification to have 80% classification accuracy. And then you need to say to yourself, well, what's the range of accuracies I'm comfortable with? So if I was it was very important for me to hit that 80% target, I might say that plus or minus 2% accuracy is the only range of accuracies that I can really accept. On the other hand, you might say to yourself, well, I could accept anything from 75 to 85%, so plus or minus 5%. And that's all very dependent upon the application. And honestly, the application and who's paying for the application, right? Because sometimes they have, for instance, regulatory criteria that has to be met. So this probably looks a little familiar to you. This is a power calculation, fundamentally. That is, how many observations do we need to make in order to get to have a probability of getting a certain accuracy. So the n, the number of points we're interested, is z squared, where z is the number of standard deviations that you'll allow. So we're going to use a two-sided confidence level of 95% error times the expected accuracy times 100 minus the expected accuracy divided by e squared, the allowable error. So if that error is 5%, then that value is 25. So let's see how the n varies with some different assumptions. So let's assume you're shooting for an 85% accuracy, but you're willing to accept plus or minus 5% error. You run through those numbers and you need 204 randomly distributed pixels. Now, maybe you say, wow, that's a lot. I'm collecting a lot of data at each one of these plots. I really need to cut down the number of plots or pixels, as it's said here. So let's say 85% accuracy, but we're happy to get a result between 75% accuracy and 95% accuracy. Well, that's only 51 random pixels. So maybe you now decide that, yeah, that's okay. I can live with that kind of uncertainty on my ultimate accuracy. Now, if I demand 85% accuracy, or I expect 85% accuracy, plus or minus only 2% error, I need 1,275 pixels. And that's, just in most cases, that's just not going to be possible. Certainly, that's the kind of study that you would have to look at using photos or high resolution imagery, and probably keeping it to simplified classes, because you can't make, once you're using imagery, you can't make as high I don't want to use the word resolution, as high a number of distinctions as you could with actually being out in the field. So ideally, you're selecting training and test polygons prior to actually classifying the data. And you're assigning polygons to training and test data sets randomly. So you distribute polygons throughout the image to capture the spectral variability or class variability. You don't sample more than twice in the same patch. And you can determine the spatial frequency of image pattern, i.e. what the size of the patches are, using a tool called a variogram. You need to sample homogeneous areas of classes. Avoid using boundaries if your goals allow that. And I'll reiterate, you should be selecting training and test polygons, because you may learn something doing the training that would bias where you select test polygons. And that's the last thing we want. What we want is to say, we need 200 training polygons. We're going to collect 300 polygons or 300 test sites, and we're going to put 100 of them away and use them only for the accuracy assessment. Okay, so how do we actually do this analysis? Well, we do it using a tool called the contingency matrix. So we go out in the field, or we use aerial photos to observe the actual land class at a sample of locations and compare the land classification as it's assigned on the thematic map. There's a number of ways to quantitatively express the amount of agreement between the ground truth classes and the remote sensing classes. One way is to construct what's called a contingency matrix, sometimes called a confusion matrix or an error matrix. This is just a row by column table with as many rows as columns. Each row of the table is reserved for one of the information or remote sensing classes used by the classification algorithm. So information class here means those based on field data. And then each column displays the corresponding ground truth classes in the same order as the classes are in terms of the rows. And that's what it looks like. Okay, so we've got ground truth values in columns, and we've got classifications in rows. And for instance, we have class B, and we went out and we made, if you go from along the row for B, we see that we collected 76 observations that our remote sensing said were also class B, and then 3 that were not. They were actually B, but the remote sensing said it was D. Okay, and summarizing that information is what we're going to be doing with the contingency matrix. So this all looks very complicated. We're going to break it down step by step. Okay, the diagonal. Okay, so the diagonal gives us the proper assessment points. Okay, so starting at the upper left, we observed a certain number of pixels. 70 of those pixels were residential and were classified as residential in the classification. Commercial, 55 points were commercial in the real world and also in the reference data. And so on and so forth, okay? Anything that doesn't fall on this diagonal is an error. You know, that is, we have 3 points that were classified as commercial, but the reference data tells us that it's actually remote reference data or remote sensing prediction tells us that it was residential. So that's an error. We then talk about 2 kinds of accuracy. One is map accuracy from the point of view of the map maker, the producer. And that's answering the question, how often are real features on the ground correctly shown on the map? So the producer is the only one who knows what the real features on the ground are and can compare that with what's shown on the map, what the actual classified image says those particular points are. This is also known as omission error. So the type on the ground is not the type on the map. Okay, the real type is omitted from the map. It's not on the map where it should be. Now, omission. Hardly anyone uses omission error or omission accuracy anymore. Okay, I just throw this in here because you might come across someone who uses the term omission error, and you ought to know what they're talking about. The way that I remember how they're talking about it is OP, omission producer. OP was a popular brand of clothing when I was a kid, and so it's easy for me to remember OP. Now let's calculate the producer's accuracy. Okay, so our reference data, which only the producer sees for the residential class says we have 73 points that we observed in the field of the residential class. 70 of those points are classified as residential. 3 of those points are classified as commercial. So the total number of reference data points we have are 73. And the producer's accuracy is 70 over 73, or 96%. Okay? So the reference data is always in terms of how many observations. So 70 divided by 73. You're always going to divide by that last row, the total row, for that particular column. On this table, I've also put the overall accuracy. Okay, so that's just the sum of the values of the diagonal, which are the correct observations, divided by the total number of observations. So in this case, that's 382 observations that were correct, divided by 407 observations that were made in total. So that's 94% accuracy. User's accuracy. So accuracy from the point of view of a map user, not the map maker. So the only thing that the map user can see is the map classes that are on the map, essentially. And the question that the user has is, how often is the type the map says really there, right? So I see forest, I see a big map of forest. What percent of those are actually forest? Or alternatively, what percent of those are not forest? This is also known as commission error. So a type on the map that is not the type on the ground, that type is committed to the map. It's on the map where it shouldn't be. Again, this is old-fashioned terminology, and hopefully someday I'll just take it off because there won't be enough people around using it. How do I remember this? CU. So Colorado University, I just remembered as CU. So there's OP and CU. And that, if I ever have any question in my head, I just line those two things up. So how do we calculate the user's accuracy? Well, in this case, we're interested in what the classification is. So we're interested in rows. And so we have on the map a class residential. 70 of those are actually residential. 5 of those are commercial, and 13 of them are forest. So we add up those 3 numbers and divide by 88. Okay, so we have 88 points that we're interested in on the map, and we want to know, of those, how many of those were correct? 70. So then that's just 70 divided by 88, or 80%. So now I've sort of got everything lined up here for you. The contingency matrix itself, a column selected from it, and a row selected from it. And one thing that's very important is you can't just look at the overall accuracy. So some classes are easy to get. Water is easy to get. In this case, water has 100% user's accuracy and 100% producer's accuracy. Well, great. I don't care, because I know water is really easy to get, and it's probably not the most important thing. If I just wanted a map of water, I just would have made a map of water. Another class, like forests, the producer's accuracy is relatively poor. It's only 74%. So only 74% of what I was looking at was actually forest, and the rest of it was residential. On the other hand, the user's accuracy for that particular class is 90%. So there are two things to know here. One of which is accuracy assessment is incredibly important. And don't let an overall accuracy fool you into thinking that the map is reliable, because it's literally the oldest trick in the book to say, oh, I'm going to put in a whole bunch of water points or cloud points and count those toward my overall classification. And that's going to hide, a bunch of errors in my other classes. I mean, this is unscrupulous behavior, but you're all adults. That sometimes happens. Now, it's not going to happen in any situation where there has to be peer review, because any remote sensing scientist is going to know that they need to see a contingency table and producers and user errors. But it's possible that in other contexts, someone might try to get away with it. Don't let them. So let's go through this process again. Here we have reference data for other classes, just F through I, and their various, the frequency of how often a correct and incorrect observations are matched up. So the first thing you would do is you would add up all the columns and all the rows and put them in their proper places. And then you've got your diagonal, so you add those all up and you add up the total. Normally you would be doing this in Excel, but it's easy enough to do if you have a calculator or a phone or just a piece of paper and a pencil, really. And you set up your producers and your users columns, and you fill them up, okay? So the users are always on the rows. It's just standard. So you're not ever going to see from me where I put the reference data in the rows. I wouldn't do that. So the user's accuracy is just the value along the diagonal for that particular class divided by the total observations of that particular class. The reference data is the diagonal value divided by the number of actual observations of that particular class. Now, and I skipped this, they don't let you go back on these narrations. What I showed you before was, instead of 0.65, I showed you 22 over 34. When you have questions on this, I won't ask you for decimal answers. I'll give you, A through D, and I'll give you fractions so that you don't have to do that extra calculation. Before I go on to K-hat index, let me tell you that on the Canvas website, under Files, there is a file. I got to find the name of the file, and my other monitor shut off, so I got to wake it up. It's named something super logical like, come on. Accuracy calculation 2020. And again, it's in the file section at the top level. So yeah, this should be easy enough for you to get at, and it's 2 pages, and 1 page gives you the problem, and another page gives you the answers. So don't look at the second page before you've done the first page. Okay, sorry for that disruption there. Okay, now we're going to talk about the k-hat index. And k-hat just means that there's a little bar over the k, but I don't write that in, I just say k-hat. So we run into a problem when we have a small number of classes, okay? Because there's a chance agreement that can inflate our accuracy figures. Let's pretend these are contingency matrix. I haven't labeled them. And let's say there's a even number of points in each box in the contingency table. And let's say I totally screwed up the classification. In fact, I'm doing no better than if I was just randomly assigning points to classes, okay? So if there's 2 classes, you got a 2 by 2 matrix, there's a 0.25 probability that a point is going to land in any one of the boxes. There's no pattern. Well, if we do the overall agreement, we're going to say that's 0.25 plus 0.25 divided by 1. We have 50% agreement. Now, 50% agreement wouldn't be great for a classification, but this effect is added on to any time that you've got a small number of classes, okay? So if you did an okay job or even a fair job, you'd still be getting this boost from the 0.25 that you'd be getting just randomly. And the more classes you have, the less of an effect this is. So for instance, you can look at the 3 by 3 classes, and there's about a 33% chance agreement that gets added onto whatever your accuracy actually is or appears to be. And then when you get to 4 by 4, you've got a 25% change accurate agreement. Again, no effect of what you've done, just randomly. So the k-hat, or sometimes called kappa index, allows you to figure out the probability that your result is better than chance agreement. And you can ignore that top equation there. All I want you to know is this, that k-hat is equal to the observed accuracy minus the chance agreement, which you get through the calculations that you're doing in the top box, divided by 1 minus the chance agreement. So we've sort of taken away the chance agreement and then divided by 1 over the chance agreement. And this shows the extent to which the correct values of the error matrix are due to true or chance agreement, okay? So in an ideal case, OA, the observed accuracy goes to 1, the chance agreement goes to 0, because you have like a lot of classes, and the k-hat therefore goes to 1. Now, k-hat can also be negative. And that means that the classification was actually worse than you would expect just given average random observations. So that's pretty bad. So I put this slide here to remind you of one thing. We have this accuracy assessment table or contingency table, and you do all these calculations, and great, now you know what the accuracy assessment is. But one of the bottom lines, I would say, is that over attention to the error matrix can mask some important facts. And that is that one of them is that the validity of the accuracy assessment depends on the testing data set. So it might not reflect properly what happens outside the bounds of the training data set. So if you have a bad sampling design, okay, you're going to get a bad accuracy assessment. If you don't follow the same rules and you do your testing data set after you've developed your training data set, then you may get results that are not indicative of what the correct accuracy is for the entire data set. There's one other thing I want to remind you of, and that is the accuracy assessment is only done on the testing data set. Okay, that's the gold standard, is having a separate testing data set that has not been influenced by the training data set and is therefore immune from any random errors that you might get in the training data set. Okay, so accuracy assessment, absolutely necessary. Don't just be worried about overall accuracy. Look at those producers and users' accuracy. And finally, don't let the accuracy assessment that you do with your contingency table keep you from looking at the actual methods that people use to generate that contingency table. Thank you.